Come to the morning session. It's a pleasure to have with us Donoghue from Massachusetts. I'm investigating about Emergent Causality and Gravity. United States Museums.
Great. Well, first, thanks to Luca for an amazing conference and an amazing venue. In the spirit of the conference, I'd like to address something that's fundamental, which is causality, and discuss the possibility that this may be an emergent phenomenon. I don't do this just to be a crackpot. There's actually some reasons for thinking that this might occur, and I'll try to do my best to give some justice to that ideas. And we already may be considering such a theory. This is work done with my collaborator Gabriel and Diego and Roberto, who are here. The caution I have to do at the start is this involves theories with higher derivative kinetic energies. The field theory of this is not complete, and I don't guarantee that everything is known here. Different methods that we normally use may use different outcomes, and so I'm using Lagrangian path integral as my starting place because that's where I start everything. I'm not going to talk here about stability and unitarity. In the question period, you can ask, they seem okay. Damiano and Selmy will talk about some aspects of this, I hope, in the next talk. And you can involve Luca in discussions on this also, since he's written some nice papers on it. But first, to set the stage. When we talk about gravity as a quantum field theory, it behaves as an effective field theory. And I'll just describe it briefly to show you what we need to do to complete it. General covariance allows many terms in the Lagrangian. The Einstein action involves the curvature, but curvature squareds, curvature cubes, etc., are all allowed. But at low energies, these higher order curvatures are negligible because the curvatures involve two derivatives of the metric, and derivatives turn into energy factors at low energies. And so in an expansion of energies divided by the Planck scale, typically you would expect these things to be small at low energies. But you can treat this as a quantum field theory by taking that first term, the Einstein term, quantizing it like Feynman and DeWitt did, doing calculations and treating these higher order curvatures as perturbations. This works because even though there's unknown physics in the world, because we don't know the ultimate completion of gravity, it's contained in this framework in just a small number of constants. The unknown physics from high energy goes into these local terms by the uncertainty principle. High energy and locality come together, and so these curvatures, the coefficients of these curvatures, contain information about the high energy theory, but they don't. But aside from a few constants, that information, since these heavy degrees of freedom don't propagate, we can do calculations at low energy just using the interactions and the degrees of freedom that we know at those energies. It's guided by this energy expansion and basically the uncertainty principle. You can use this to make predictions. That's not my focus in this talk, but you can make the quantum correction to the Newtonian potential, to light bending in the Eichenal approximation. The ones I showed you there are independent of any of these unknown parameters. The point that's more relevant for today's subject is how this falls apart at high energies. And there's two things that come together, but they're really independent. One is that these higher curvature terms become more important at high energies. You have an infinite number of them, in principle, and they then go off in an infinite number of directions, each one blowing up infinitely more than the previous one, if you go to high energies. So you lose total control over the theory at high energies. Moreover, even if you knew the coefficients, well, you can't get rid of these coefficients naively within the effective field theory framework, because you need all these coefficients for renormalization. The divergences that you find in the theory are local. They can be a local counter term, like the photon is the Weyl tensor squared. Weyl tensor is just some combination of curvatures. That one loop in harmonic gauge, the classic coefficient of total development. Two loops, we also have the author of that heroic calculation here. You get curvature cubed, etc. So you get all orders of the energy expansion from doing this. So even if you knew all the renormalized coefficients, you'd still have troubles with the theory blowing up at high energies. Okay, so we have two troubles. In the end, I'm going to come back to a theory which looks very similar, except it's quadratic gravity, truncated at curvature squared. So I've just dropped all the higher order ones. This is now a renormalizable field theory for gravity. It's not treated as an effective field theory in principle. In practice, what that means is that I have four derivatives in curvature squared. I treat those four derivatives fully and don't treat them just as perturbations. That means the propagators have an improved, they can be renormalized, the propagators have improved high energy behavior, but with that high energy behavior comes dangers. The theory is possibly asymptotically free in both those couplings. Depends on the ratio of the parameters, but that's a possibility at least. That's also not the focus here, but you could, if you want to talk to Diego and Roberto more about that also, that's fine. So what I'm going to do for you is three calculations. These were enlightening to me. I hope they'll be something for you. We're going to talk about this idea of emergent causality. I'll show you how effective field theories work in this framework, which surprised me, and then some cancellations that are going on. So here's the basic calculation. Let's take a higher derivative scalar and couple it up to matter of some form. Okay, there's some matter coupling down there to it. And the two derivatives and four derivatives is the thing we're focusing on here. This is slightly a busy slide, but let's just do it quickly because it gets us to the heart. If I want to do the path integral over that field, coupled up to something, I can remove the higher derivative operators by using an auxiliary field. The underlying parts in red is a Gaussian integral, which reproduces the first term exactly. And then if I redefine some variables, I'll just change variables. This particular structure factorizes. So I get a massless field coupled up to these external particles. And I get a massive field, a normal Lagrangian for a massive field coupled up to the particles. The trick and the danger here is that one of these has e to the is and the other has e to the minus is. So the second path integral, even though it's also a Gaussian integral, has the opposite sign of I on it. That causes troubles. One way I'm going to now take you through why that causes troubles. So the issue here is it's going to violate causality. The requirements for causality, we know the operators commute a space-like separation, and that's generally the statement that you hear, but you also have to have a sense that all the fields share a common past and future light cone. And that is encoded in the I epsilon. And you can see that when you do something like the Schilling-Lemon representation for propagators. but it only comes with a plus I epsilon in my case. Minus I epsilon by itself would also work, but you have to have the same I epsilons for everybody. If you don't, you end up with causality violations, and there are explicit calculations which I won't go through. But you can see why. The I epsilon prescription tells you about the past and future light cones. In particular, the usual one that we use takes positive energies and propagates it forward in time. So if you break up the propagator into time orderings, positive energy propagates forward in time with this I epsilon. The point here now is that the e to the is and e to the I epsilons are tied together. In fact, when you do path integrals, the only place that I enters physics is in the e to the is. That's where it enters physics. And so if I was to do a path integral with e to the minus is instead of plus s, I get slightly different results. I basically change my factors of I. The easiest way to see this is the time reversal operation. Time reversal is anti-unitary, which means that you not only change your fields, but you complex conjugate everything. And so if you are working on a path integral with an e to the plus is and complex conjugate, you get e to the minus is. E to the minus is corresponds to the time reversed situation of plus is. If you just did it overall to all fields, it's just changing your clock direction. But if you do it for some fields and not others, then that's when you get in trouble. So the time reversed, if you use e to the minus is, you basically change the factors of I in the propagators. You can do this calculated directly by doing the Gaussian integral. Let me skip that in the interest of time. But basically the message is that if you use e to the minus is, you get the time reversed process. If I define positive energy in the same way that I did before, this guy propagates positive energy backwards in time. That's where the trouble arises. And you can see this directly in the propagator. I mean, these things, I've added a decay with these things actually decay to these light particles. But if you analyze the propagator that I put up above, you avoid tachyons by choosing m squared positive, and you find holes at funny locations, but basically with factors of I reversed. So, what's this about emergent causality? So there's causality violation, and that's the way it was normally phrased. This idea goes back to Lee and Wick in the 60s. But you can also, since this is a heavy field, you can form the effective field theory from it by integrating out the heavy field. In this case, it's a Gaussian integral. It leads to a contact interaction of low energies and just shifts the lambda phi to the fourth coupling. Okay? It has that minus sign, which is a little bit destabilizing, but if the field is heavy enough, you still have a positive lambda. So the low energy theory of this is just the normal field theory, in this case of a massless particle interacting with normal matter, and with the normal causality structure. So you have no causality at high energies, you do have causality at low energies. So this is, I argue, a generic feature of higher derivative theories. If the heavy particle generally will have this separation into a normal particle and a heavy ghost, you can integrate out the heavy ghost and potentially, at least in some cases, arrive at a normal low energy theory. The early work by Lee and Wick is somewhat harder to penetrate. There's this wonderful paper by Grinstein, O'Connell, and Wise, where they've used the phrase emergent causality, which I think is the right way to think of it in modern terms. But if this is at the Planck scale, then perhaps this can be a allowable change consistent with low energy theories. Okay, so that's the emergent causality part. Now, here's calculation number 2. I want to show you what happens when you do this theory as an effective, when you use higher derivatives on an effective field theory. So here's an effective field theory that I've written down here. It has a shift symmetry. You can shift the field by a constant, and you can use that symmetry and write down all higher orders. In fact, those derivatives there means it's not renormalizable. It's like gravity in a way. You get dimension 4, dimension 6, dimension 8, all higher powers. And the parameterization g over m to the 4th capital M is just there to give you a sense of what the mass dimensions of things are. Viewed as an effective field theory, you would think it breaks down at basically m, somewhere around the capital M. And you can do calculations in this theory, and there's a one loop scattering amplitude. You get the lowest order one, you get the next one, you get the dimension, the 8th, so ST and U are the Mandelstam variables, basically energy squared, and so that's energy to the 8th at the bottom. It behaves like an effective field theory. Now if we add one of these higher derivative terms, now it's coming with this lowercase m. It's a renormalizable field theory now, and so we can do calculations. Here's the result from the calculation of the full amplitude at one loop in this theory. It seems much more complicated, but in fact it simplifies quite nicely. At low energies, it matches the effective field theory. It's a good example of effective field theory. It was renormalizable. It predicts all the coefficients in terms of the parameter, the coupling constant, and the masses. So it's an effective field theory. What's interesting for us, and was a surprise for me, is how it simplifies life at high energies. So now, once you get beyond this lowercase m, the scale of the higher derivative operator, it becomes simple again. That whole thing collapses. All the dimension 6, dimension 8 terms that you found in the effective field theory disappear totally. There's no more dimension 8 in the answer at all. It just comes back down to the starting point of the original interaction with a running coupling constant and a few logs. So it's simplified dramatically, and all the terms that we worry about in effective field theory have disappeared. That's the phenomenon I want you to remember here. And I also want you to remember that it happens not at the capital M, which is where the effective field theory was going to break down, but perhaps earlier, driven by the parameter that parameterizes the higher derivative term. We can understand it actually. It's actually going to be a general feature of such theories. The way to understand it is to shift to these dimensionless fields by just basically putting the only dimensionful factor into the first term, the two derivatives. Then when I go to high energies, I can drop the two derivative piece, and I can calculate in this theory and get just the right answer again. There's no dimensional factors here, so you don't have any dimensional factor to generate the higher derivative terms. Once you neglect that low energy piece, it's scale invariant. Okay. That was calculation number 2. Calculation number 3 is cancellations in models like this. We saw that the coupling was in that original model. The external field is A minus eta. That was A minus phi was A minus eta. And so these two fields actually enter with opposite couplings. They then cancel in many processes. And Bob Holden was the first to point out, he's doing the same calculation that we just did of this higher derivative scale shift invariant model. And he finds that if he does inclusive calculations summing over the A and the etas, that instead of blowing up, because it was going like energy to the fourth, it falls off. There's extensive cancellations, and in fact, it's well, I can't quite defend everything that Bob does. Here's a calculation in quadratic gravity that I've done, which basically ends up being the same thing. You're producing the scattering through the spin 2 channel. It has the normal particle and the ghost, and at high energies there's cancellations. We're working to try to see if this is a robust feature or not. So this is the weakest part of what my free calculations, because I don't feel like I can defend this totally in public, but I'm going to, for the purpose of this talk, accept that. So here's the picture that emerges. If you have these high derivative theories, you have this phenomenon of emergent causality where the usual low energy theories have usual causality, but there are new Feynman rules at high energy. They simplify the effective field theories, in particular that whole tower of operators is gone, and they possibly become weakly coupled above the scale of this high derivative. So that's the framework. Are there such theories? Well, I'm going to make the argument that we're considering one already when we talk about Starobinsky inflation. Starobinsky inflation is the theory that's treating R plus R squared not as an effective field theory, but as a real dynamical theory. There is the extra degree of freedom in the curvature squared term. That's the piece that's responsible for ending inflation. The argument now goes that since these terms, these interactions mix under renormalization, that it's inconsistent to consider just R plus R squared. You need the Y squared term also for consistency. Because if you change your scale by a little bit, you'll mix the operators. If you do that, that brings you to this theory of quadratic gravity. So we're considering, I'll come back to this a little bit. There's the theory and there's the beta functions. There's also a sense that this is natural in a more general class of theories where you use Wilsonian renormalization group ideas, where the renormalization group flow brings in operators of all dimensions. And in particular, in gravity, you can't exclude the R squared and Y squared terms because they come in under renormalization group flow. This is the part of the asymptotic safety program, but is in fact more general. The argument that I've said now raises the question of whether renormalization group flow in the Wilsonian sense would generate such terms in a renormalizable theory like the standard model. And the answer, of course, has to be no. That the renormalizable theories are self-contained and predictive. So they predict everything, and their higher derivative operators could be more innocuous. They could just be things like the expansion of the log of logs. And Leslie has pointed out that this is a way to avoid some of the problems of theories with higher derivatives if it's really innocuous running like that. But effective field theories can't do that. Effective field theories bring in these running in a much more hard way. And the theory that I described earlier has actually been analyzed using the functional renormalization group by Diego and Roberto. But, so, with that, let's just take a quick look at quadratic gravity. It's the Weil square term that's the most dangerous piece here. That's the one that gives you the ghost. By chance, the curvature, scalar curvature squared term, the ghost is actually the graviton gauge artifact. So there's no ghost there. But the spin 2 piece is a piece. The basic thought here is that if Starobinsky inflation is going on and is completed by the Weil squared piece, then we may be in a situation where this is, at least temporarily, a renormalizable field theory that, as we approach the asymptotically correct theory, could be a closed, self-consistent layer of reality. Just like the standard model, we have the standard model. We don't think it's the final theory, but it's, for now, it's closed, self-consistent, and can be propagated well beyond the electroweak scale. Here, if you did the same thing at the scale of inflation, you would end up with this quadratic gravity theory and propagate it to higher energies in principle. But at least temporarily could be a renormalizable theory for us. But this changes our picture quite a bit. The feature here, the most interesting feature, is that the theory changes at the Starobinsky scale, which is 10 to the minus 5 of the Planck mass. Nothing particularly happens in quadratic gravity at the Planck scale, and you can see that in these scattering cross sections here. The Planck scale, this is in units of the Planck scale, and nothing happens there, and everything happens earlier. It turns over and becomes weakly interacting. This is a little surprising because of our way of normally thinking that everything happens at the Planck scale, but it's also what happened in the electroweak theory. In electroweak theory, when we had the Fermi interactions, we could do the scattering of longitudinal gauge bosons, and it violated unitarity at 1.6 TeV in one of the channels. So that 1.6 TeV was sort of a place where this thing became strongly interacting, except that it didn't. The Higgs boson came in an order of magnitude below that, and turn the theory into a weakly interacting theory, and nothing happens at 1.6 TeV, it's just normal theory. So this is the same sort of feature that the Higgs did for the standard model. So this could be useful in the theory of inflation. One of the things you worry about is field excursions beyond the Planck scale. Here, the Planck scale doesn't have any particular role. This is, in Starobinsky inflation compared to others, it's a much more innocuous extrapolation. And it may also help with the initial conditions for inflation, which many people complain about. Inflation was designed to solve the homogeneity problems on large scales, and but it requires homogeneous initial states to start inflation. The causality violation should perhaps help with that. But of course, I'd be disappointed if this was the case, and then we couldn't see a signal. So the goal clearly is now, if we take this as a serious framework, to look for causality violations in the early universe. If causality is such an important property, we should see some signal of it if it's violated. I don't have the definitive one now. The obvious one is correlations outside of the light cone. But in the early universe, it's hard to know what the actual light cone was. There's possible going to be evidence for biosquared, and Luca has done some work on this, and if you could ask him in the question period. There's a new paper by Bianchi, Morel. Anyway, there's also in this theory a different cosmological solution, which can be superluminal. It's sort of a slow roll expansion. I don't have time to describe it, but I think it's interesting. I will skip that, and I'm going to go straight to the summary because that's what my chairman says. This idea could be a frontier for the high energy limits of some theories, in particular for gravity. It's remarkably simple to achieve and potentially even natural in the framework of Wilsonian mineralization group. We are considering such a theory when we talk about Starobinsky inflation, and there may be advantages. And so the question is, we have this relatively simple theory, which could at least be a temporary renormalizable regime for gravity, has this amazing feature, and can we see evidence for it? So let me stop there.
Thank you, John. It's time for question. Yeah.
Thank you. I have a sort of a little bit conceptual question, because you very nicely explained how this degree of freedom propagates energy backward in time.
Yes.
So basically, you have a theory that at some short distance it doesn't make sense, but then you're saying, to me, if here doesn't make sense at one scale, it doesn't make sense at any scale.
Well,
but you are saying somehow you can integrate out.
That's the idea, yes.
But how can you integrate out the degree of freedom that propagates backward in time? Normally, we integrate out normal degrees of freedom, not the.
Yeah, well, I mean, I did it for you there in the path integral. The path integral for the particular example that I showed you was just e to the minus is for the Gaussian integral.
No, I understand, but that's. I don't think that is clear that applies to the degrees of. It's like saying that theory tells you 2 times 2 is not 4 at one scale, and then all of a sudden it becomes 2 times 2 is 4.
It's not 2 times 2 is 4. That's mathematics. There's some Feynman rules here. You apply those Feynman rules in a more or less standard way. I'm not going back into all the field theory, but in a more or less standard way, you apply those Feynman rules, and it leads to things like scattering amplitudes, and,
no, I understand
and you can take the low energy limits of those amplitudes.
No, that I understand, but there must be some common sense, because you are saying if I compute in a full theory,
yeah.
I have a degree of freedom that gives me trouble. Well, and now how can integrating it out change it? I mean,
because it's massive and only propagates a long distance and it's unstable. It's not an asymptotic state. It doesn't live to the asymptotic state.
No, that's not true.
Yeah, it does. It does. It decays.
No, the ghost degrees of freedom, they do not decouple.
But they decay. Those are unstable. Yes, they are.
No, you cannot treat them as normal particles. They are nonsense. So it's like saying that you have a degree of freedom which doesn't make any sense, and I treat it as a normal particle. I mean, this is a conceptual question. I'm not doubting the practicality.
It's actually a calculational question of whether the calculation makes sense. I'm starting with a Lagrangian path integral with this guy in it. And at least up to one loop, I can make sense out of it. At higher loops, I don't know how to do some of the integrals because of overlapping divergences and analyticity issues, which Damiano might tell you some more about. But but at least up to one loop. And also there have been a lot of simulations of such theories that indicate stability. So, I mean, I'm prepared for it to die. I wouldn't mind it dying, frankly, but as far as I can see, it seems to be a strange but functional theory.
Thanks for the guest. I was wondering, so you have been desired deliberately is this violation of causality at the short distance scales, but what is the mechanism that prevents these causality violations from building up, accumulating, and become large scale?
It's something to worry about. There's no evidence that it does. I would look at the calculations to try to see it. You don't see that happening. In a way, this integrating out makes the argument that it shouldn't happen, because if you can form a normal theory by integrating it out, you end up with the low energy theory, which is a normal theory, with the only causality violation things would be suppressed. One of the slides I skipped over is existing ideas for testing it. If the scale is very high, like gravity, none of these ideas have any applications. These were ideas for ones where you're at the scale of the ghost. But if you were able to come up with a way that this builds up, that would be interesting and perhaps devastating.
It would be just an expectation that it builds up, but so for instance, if you integrate out the theory of freedom and then you extract the energy with some coefficients, would they satisfy causality bounds?
No, in fact, that is actually one of my things, is the theory would have opposite signs on some of the effective field theory coefficients, and so they would not satisfy causality bounds. But that's because causality wasn't an appropriate assumption to make for the original theory.
So actually I have two questions, and maybe I ask the first one. So to get to Gia's point, so if I think of, one can think of both either as like negative norm state or negative kinetic energy state. But if I think of kinetic energy being negative, then naively it seems that large mass will not protect me, because normally when mass is large,
So
you can't reduce. But of course with negative kinetic energy you can reduce.
and that's right. So you have those two choices, and the correct choice. One of the choices, if you choose the parameter of the wrong sign, leads to terrible instability, because basically everything decays into even space-like. So you'll have poles of space-like momentum, which then leads to everything to decay into. That's the tachyonic case, and that is avoided by choosing the sign on the parameter. This one is positive energy. You can see it's positive energy because it's produced by scattering two of the normal particles. When you hit that resonance, you've taken normal particles and hit a resonance. And so the interpretation is that it's a positive energy state with this funny time propagation behavior.
Thanks.
More question or comments? So I'm just a comment maybe from the point of view of the scattering relation, this opposite direction prescription, can you always treat it as regular time prescription plus a delta function that eventually produces in class?
Yes.
Be seen in this way rather than
Yes.
going through the part integral is better looking at it as Fourier transform or something else.
Right. There's also ways to write dispersive representations of this that Coleman wrote back in the Leawitt days that make that manifest actually.
Then, okay, I don't see any comments or questions. Let's thank John